Hello everyone, in this video I'll explain questions from practice exam 3. Okay, so let's start from the first one. Okay, so the first one is about, right, let's start reading the question. When a sealed 1 liter flask charged with many moles of iodine than 0.5 moles of bromine. Okay, and then as you're reading, right, so as we're reading, that's right, those information about the reactants. Okay, so then quickly we start with, right, this is a good habit. Okay, what's given? Okay, given information is that we have iodine, which is initial, right? Initial charge, you put it in there, right? So that's initial what you have, and then that's how many moles. But we also understand, right? So type of calculation in a sense that you already read it, you will read the reaction will reach equilibrium. So then again, for ice table, right? So we need concentration. So moles, we need to turn the information into molarity. Okay, so molarity will be moles divided by liter. Okay, so we do that, then we got 0.5 molar. Okay, then we can do the same calculation for bromine. Okay, so that's also initial concentration. The calculation will be the same way. Okay, so then that'll be 5.5 molar of bromine. Okay, and then the other hidden information is what? Since we said we only have those two start off with, so then that's also implied, right? The initial concentration of the product is 0, because right, I have none of that. Okay, and what else we know is that, let's see what else. We have information about at equilibrium, right? After achieving equilibrium, we have the concentration for IBR, okay, so which is at equilibrium, which will be 0.84. We're gonna do the same, right, calculation. So that's 0.84 molar. Okay, so that's all the information we know, and now we're looking for equilibrium constant, which will be KEQ, where you go KC, right? That's normally that's what we use to express. Okay, so very clear, right? We have to set up as table, and then for me personally, I do like to bring my balance equation. Okay, the importance of that is that I will now forget the stoichiometric coefficient, right? That's how reaction proceeds, and then the reaction reacts to that ratio, okay, and then during change, right? So change is how the reaction, right? How the reaction goes. Okay, so now if we know that, I'm gonna set up as table. Okay, so initial and all of that, we have already figured those information out. So then let's start to plug in the info. That's 0.5, 0.5, initial of that, 0. Okay, and then at equilibrium, we have the concentration of the product, or 0.84. Okay, and then you go which way direction goes. Okay, so for this type of question, of course, we can calculate Q. Okay, Q for the initial, right, was products over reactants. Products is 0, so then Q is actually 0. Okay, and then you go, I don't know K, we're calculating K, but think about it, right? K has to be bigger than 0, and then if Q is 0, K, no matter what, right, is gonna be bigger than Q, right? And then in other words, if you look at it, initially you only have reactants. Which way this reaction has to go? Only has the way to go is to go to the product side, and therefore the change will be negative, negative, positive. Go by what ratio? It's 1 to 2 ratio. So over here that'll be 2x. Okay. So then let's put that. Then you go. Now what? Right now, let's see. This column, right, is fulfilled, which means you know initial, you know final, and the change equals to 2x. Do we get a relationship? I believe so, right? So then therefore we know that 2x equals to 0.84. So x equals to 0.42. Okay. So then if x equals to 0.42, I believe we can just swap off this, right? 0.42. 0.42, so therefore we can calculate the concentration at equilibrium, which would be 0.08, 0.08. Okay, and then again, now we can use the information at equilibrium, calculate that KEQ. Okay, KEQ will equals to products will be the concentration of IBR at equilibrium square. Don't forget to square, okay, because the coefficients was 2. Okay, divided by the concentration of iodine at equilibrium times concentration of bromine at equilibrium. Then we're gonna plug the information. So that will be 0.84 squared divided by 0.08 times 0.08. Okay, this calculated comma is 110. Okay, so then that's why the answer is C. Okay, so that's for the first question. Now let's look at the second one. Okay, the second question is giving us KC, right? Giving us KC value, so we know what the equilibrium constant at, right? So what the KC is. Okay, so the analysis given, and then it's asking us to calculate the number of moles of each component at equilibrium. You go, well, remember, right, when we use as table, we're using molarities. Then you're, oh, if I know volume, I can calculate moles, right? Okay, so remember that. And then let's keep on reading. What else we know is that we know this, right, equilibrium is obtained from, so which means all of the information, let me use a different color, okay? All those information is for initial, right? Okay, so the next initial, then you also see moles and the liters. Like, okay, I can calculate molarity. Of course, that volume I can also use to, at the end, calculate back to the moles at the end. Okay, so now I think I need a new page to solve this question. Okay, so we need some more space. So let me copy paste this. Okay, so then this question. But this question itself actually, right, is the same logic in the sense of, right, we have KC, we're looking for information at equilibrium, we know what to do, okay, but then just give the info slightly different, know what, right? So the way thought process is the same, but slight, right, little details gonna be slightly different. Okay, so as I said, what's given? Okay, given info is that we have 1 moles of hydrogen in 5 liters. So clearly we can calculate the concentration, initial concentration for hydrogen by doing 1 mole over 5 liter. Okay, this will be 0.2 molar. And now we're gonna do the same calculation. Initial concentration for CO2 will be 2 divided by 5. Okay, that'll be 0.4. Same way to calculate for water. That'll be 0.750 mole divided by 5 liter. So then that's 0.15 molar. Then the initial concentration for carbon monoxide, that'll be 1 divided by 5. Right? Okay, so after calculate, I got 0.2 molar. Okay, now, right, you got the initial concentrations. Very good. Okay, so then you go, okay, which way direction goes? What's the drill? We need to calculate Q. Okay, so Q, how do we calculate Q? Q will be products over reactants. Okay, so then products will be water times the concentration of carbon monoxide divided by concentration of hydrogen times concentration of carbon dioxide. Okay, plug in the we just calculated it. 0.15 times 0.2 divided by 0.2 times 0.4. Okay, as I calculate, I got 0.375. Okay, we're supposed to use this number to compare to KC. Okay, KC is given from the question, which is 1.60. Okay, so then therefore we calculated KC smaller, QC smaller than KC. We know the reaction will proceed to the forward direction, which means what? The reactants don't have negative sign because you're using it, consuming it. Okay, and the products don't have positive sign. Okay, so because you're making the products. Okay, once we understand all of this, that's read the equation. Actually, I'm gonna copy and paste it. Now we're gonna set up as table. Okay, so that's what we have as table. Okay, I'm just gonna directly write it like this. Okay, in nature, what do I have? 0.2 because that's again the ice table is based off concentration molarity. This will be 4. We calculate it, right? Okay, look at the numbers, and then in nature have 0.150. This will be 0.2. As we already interpreted, right? So reactant's gonna have negative signs. It's negative, negative. This will be positive, positive. right? So negative x, positive x, and x. Okay, and then at equilibrium, what do you have? 0.2 minus x, 0.4 minus x, 0.150 plus x, 0.2 plus x. Okay, so we have this at equilibrium now. This will equals, we can express Kc. Okay, Kc will equals to products will be 0.150 plus x times 0.2 plus x divided by 0.2 minus x times 0.4 minus x, which equals to 1.6. Now what? Clearly, this question, small approximation is not going to work because that Kc value is quite large. Okay, and then this question, you have to rearrange it into the way we can use quadratic formula. Okay, so I rearrange it about 0.60 x squared minus 1.31x plus 0.098 equals to 0. I'm going to use quadratic formula. X equals to 2a negative b plus minus b squared minus 4ac. Okay, so now we just need to plug all the information in, right? 2 times 0.60, and now be positive 1.31 plus minus negative 1.31 squared minus 4 times 0.60, c will be 0.098. Okay, then do the calculation. We'll get x equals to 1.31 plus minus 1.2169. Okay, and then we'll get two solutions. One is x equals to 0.0776 or x equals to 2.11. Okay, and as we go, the two solutions, what do? You see if both of them make sense in the question. And then in this question, this 2.11 doesn't make sense because if you put it back into our ice table, right? Okay, if I have 2.11 over here, what's going to happen? This is going to have negative value. Again, negative concentration doesn't make sense in chemistry. Okay, so then that's why this will be, right, we can get that out of the way, right? So then that doesn't make sense. So we're keeping this, okay, and then we can calculate the concentrations at equilibrium for each reactants and products. Okay, so therefore the concentration will be 0.2 basic plus x back into our x table over here. Okay, so I'm plugging it in actually right over here. Okay, so then it will be 0.2 minus 0.0776. Then I got 0.122. Okay, and then you go, is it done? We're calculating moles. So then you can calculate how do you calculate moles? Concentration times volume. So concentration times 5, then this will be 0.610. Okay, so that's how many moles. And now we can do the same calculation for the right side. So I'm just going to quickly write this down. So that'll be 0.4 minus 0.0776, about 0.322. Then moles of that CO2 will be 0.322 multiplied 5, got 1.61. Okay, and then the next one will be water, will be 0.150 plus 0.0776. Then we got 0.228. Okay, moles of H2O will be 0.228 multiplied 5, about 1.14. That's how many moles. Last one, concentration of carbon monoxide, 0.2 plus 0.0776 gives us 0.278. Then moles of carbon monoxide will be 0.278 times 5, give us 1.39. Okay, so now we got all the answers. Again, really it's now about, okay, all of this busy work is about you understand what you need to use to calculate throughout the question, and then how apply to that particular question, still get to the correct answer. Okay, so that's for that. And now let's look at the other question real quick. Okay, so then the question we're given with case C, okay, 0.11, clearly this question, small approximation, doesn't work again. Okay, but let's keep on reading. Okay, so we are calculating the equilibrium concentration of this. Okay, and then we are given with this 2 initially. So then quickly we realize initial concentration of those 2 products were given. Okay, but it's not concentration the most, and later we have been doing this, so then you know the drill, right? So they got, at this got 0.225. We can calculate the same for chlorine. So it's also 0.225. Okay, and then again, this implies what? The initial concentration of ICl is 0. Okay, and if so, right? Okay, and then we are looking for equilibrium concentration. We know S table is needed, right? Okay, so then let's set up S table. Okay, we're looking for the concentration of ICl at equilibrium. Okay, so that was initial. So then let's bring our equation. Okay, then S table. Initial is how much? 0, as we said. And then initial is 0.225, 0.225. Okay, so now important is how do we determine the change, which way the reaction goes. You can calculate Q, right? Q is products over reactants. Products is what? 0.225 times 0.225. Reactants, right? It's 0. So this number is infinite, large, infinity, right? So then this definitely is gonna bigger than K, and K is only 0.11. So therefore, the reaction goes to the reverse direction. So then this will be negative, negative. So which means you're gonna consume those products, and then the reaction goes towards reactant. Okay, so then this will be 2 positive. The reason why it's positive 2 because goes by the coefficients. Okay, so now we got this information, we can get what's happening at equilibrium, right? So this is 2x 0.225. Right? This was x minus x and minus x. Okay, so now you get the information at equilibrium. We know equilibrium, how to express that. So Kc equals to products. That'll be 0.225 minus x times 0.225 minus x divided by dr, reactants, right? It's raised to its power. So 2x raised to the power, which equals to 0.11. Again, we quickly realize on the numerator what happens. This is actually, since it's the same, so we can turn it into a square. So if I have square here, we can take a square root on both sides. So then therefore on the left, I have 0.225 minus x over 2x, or equals to square root of 0.11. Okay, so then you solve for this, and then x will equals to 0.135. Okay, and then is this our final answer? No, remember, that's what we're looking for. So what's its concentration gonna be? 2x, right? 2 times 0.135. So we got 0.270. Okay, so then therefore the answer is C. Okay, so then this is the video for these questions, and thank you for listening.